Hi everyone, this is Mr. Chu again, and I'm going through the key ideas on forces and dynamics and techniques, things that you need to be very sure of so that you'll be able to solve questions. What I'm going to go through are the fundamentals of handling questions on forces and dynamics. So even though it may not seem very complicated, but it sets the foundation for you to do the questions properly. So the first thing which some of you may think that it is trivial is to be able to identify the kind of forces that acts on a body. Now, first of all, you need to be able to identify the various kinds of forces that is in your syllabus. Of course, other than electric force and magnetic force, which we'll cover later. The typical kind of forces that you'll be handling are weight, normal contact force, air resistance, friction, upthrust, and tension. Not so much of upthrust, but the 5 over here with the upthrust. Because upthrust is very obvious. If you are inside a liquid, then upthrust will become significant. But of course, if you're in air, most of the substances where we have and we handle, which are solid, upthrust is not that significant in air. So upthrust becomes very apparent, so I will not cover that too much in this micro lesson. So for weight, you need to know, it is very trivial, but you need to know that weight is always downwards, and normal contact force always perpendicular to surface. Trivial as it seems, it becomes very important later on. Whenever an object is in contact with a surface, there is always normal contact force, and it is always perpendicular to the surface. Now, whenever you can say the word always in physics is really important because it's unchanging. In whatever complicated situation, it is always true. Air resistance, it's always opposite to velocity. This is always along the surface, and opposite to motion. Okay, when we just like elaborate a little bit more over here, motion, it doesn't mean the motion of the person. Say for example, if a person is over here and walking forward, the person is moving forward, but the legs are kicking on the ground backwards, and therefore the frictional force is forward, enabling you to move forward. So it's something very intuitive. You kick backwards, you move forward. Because you exert a force on the ground backwards, the ground exerts an equal and opposite force on you forward. So the motion over here is on the ground, where it touches the surface, not the motion of the whole body. Just like a wheel. The wheel rolls forward, but it kicks on the ground backwards, and that's why the ground exerts a frictional force on the wheel forward. So you need to be very careful that when we talk about opposite to motion, it is opposite to the push or to the kick or to the tendency of the motion at the point of contact. So you have to be very mindful over here. Upthrust, of course, it's upwards. Tension, this is trivial, seems very trivial, but you need to be very careful over here that it is always pull. Always pull. So whenever I have an object, if I have two objects being tied together, A and B, and if you want to draw the free body diagram of body A, the tension over here on the right side will be T1, and the tension on body A due to this string over here is T2, it pulls A. Whereas that for B, it pulls on B, it never pushes. So it's always pulling, you never tie a rope around something and push. So we are establishing the basic nature of these forces and type of forces that we're handling, and let's apply it to drawing free body diagram on a couple of scenarios so that you know how to handle this the interpretation of scenarios better. So because once you are able to identify the forces, draw the correct free body diagram, then you are able to apply the Newton's second law, the F equals to ma, which is an interpretation of the Newton's second law, properly. Because if you get the forces wrong, the direction wrong, then you will be in you have issues. Okay, so let's take a look at this situation, the one where you have an object on the ramp. Then we'll look at one of the example that students always have issues with, which is person in the lift. Then we'll go through a more complicated version of that. So let's take a look at the ramp and the box. So ramp and the box. So on the box, let's take a look at the free body diagram. On the box itself, weight, remember, we talk about it always downwards. And of course, if you're talking about the situation where the box is stationary up there, now the question is, some students will think whether should I draw this force over here? No need. Because once you draw this weight over here, it is already comprising of this component and this component. Okay, so you don't need to draw the component of the force over here and over here. One weight will be enough. And remember, whenever anything is in contact, there's normal contact force and it's perpendicular to the surface. If you have an object over here like this, it will not stay still. It will slide down. So you need, because it tends to slide down, it opposes the motion this way. Okay, so how about the ram itself? How about the forces on the ram? Of course, the ram itself has its own weight. Okay, now then the question is, does the weight of the box act on the ram? Now this is the interesting part. You have to be very clear. You have to be very clear with the description of the forces. The weight is the interaction between the earth and the box. It has nothing to do with the ram. But the interaction between the ram and the box is the normal contact force. So the force or the influence that the box has on the ram is the normal contact force, which is here. The force by the ram on the box is upwards towards the north, if we may use this system, northwest. So the force by the box on the ram will be southeast. Okay? Same. If the frictional force by the ram on the box is upwards, the frictional force by the box on the ram will be downwards. Alright, so this is the free body diagram for the ram and the box. So the other thing that you need to know is that whenever an object is at rest, you need to be able to draw a free body diagram comprising of the three forces such that they form a closed triangle. Let's apply it to this one. You'll find something interesting. This is the weight of the ram. This is the frictional force this way, and then you've got a normal contact force. So how? Can you see that you can't really form a closed triangle? There seems to be this gap over here because we missed out one, which is the normal contact force by the ground on the ram. Okay, so it must force itself to close the triangle eventually. It must be, in fact, it must go all the way up there. Alright, so these are the things that you need to know. Identify the forces acting, follow the rules, the nature of the forces, normal contact force perpendicular to the surface, weight always downwards, and then you need to, if an object is in equilibrium, it must form a closed triangle. Okay, let's take a look at the situation over here, which you have the person in the lift. Now I'm going to throw in something else in this question, which is the magnitude of the forces. If a person is building on what you have watched just now, if a person is moving up but slowing down, remember we talked about this, that whenever an object slows down, what does it say about the acceleration? The acceleration is opposite to the motion. So the acceleration is pointing down. Now let's take a look at the free body diagram on the man and on the lift. Obviously there's a string pulling it. Let's start with the man first. So the man, simple. And the man is in contact with the flow, so there is a normal contact force that's perpendicular to it, so it will be this way. Now there's something wrong with this diagram. Probably I pause for 2 seconds and 3 seconds. Take a look. What's wrong with this? Knowing that the acceleration is downwards. Now if the acceleration is downwards, it means that the net force must be downwards. It means that the weight must be more than the normal contact force. And therefore, the length of the arrow must represent that. The arrow with this is that the normal contact force is longer than the weight, meaning that the magnitude is bigger, which is wrong. So it should be shorter. The examiner will not go all the way to the point that it will measure, but it must be visible. Okay? So these are the two forces acting on the person, tension for the string that's pulling it up, and there is a weight of the lift. Now again, remember the example just now, the weight of the man, does it act on the lift? If it doesn't act on the lift, then what's the effect of the person on the lift? Because if the person is in the lift and the person is not in the lift, it does make a difference to the engine that's pulling the lift up. So it must have an effect, but is it the weight of the person that it's supposed to be included inside here? Think about this, the weight of the person is the interaction between the earth and man. It doesn't have anything to do with the lift. So what's the force that the lift exerts on the man, or the interaction between the man and the lift? is the normal contact force. So the normal contact force is the force that the lift acts on the person, so the person exerts an equal and opposite force on the lift. And in fact, if the acceleration is downwards, I should draw this one shorter so that it is definitely true that this plus this is bigger than this. And you will notice that actually I draw this one from the center of gravity. I draw this one as much as possible close to the center of gravity of the person, and the normal contact force at where the forces act. So it is important that we take note of all these things, the magnitude and the position where the force acts. Okay, so these are the some of the very basic tips that we need to know in order for you to solve the questions properly. Because a lot of students think that they cannot solve questions because, of course, some students have conceptual issues, but sometimes it's because of these fundamental lapses, or you don't have a good grasp on the fundamentals in solving problems. That's why the rest that follows will have issues. So you need to know the kind of forces that you're handling in any scenarios, draw the forces properly, and then eventually be able to write the equations effectively, which I'll cover in the next videos. Alright, hope that this is helpful to you. Thank you.